Swayam Prabha. Digital India. Educated India.
So essentially what we have a correlation for Sherwood number, which contains mass transfer coefficient in terms of operating conditions like Reynolds number and Smith number, and of course this correlation, as we said earlier, has to be determined experimentally. So we can write Sherwood number as Km some characteristics length divided by the diffusivity equals A Reynolds number to the power some coefficients small a, Smith number to the power b, and maybe there are other parameters here. So what we have to do is to calculate Reynolds number and Smith number under the operating conditions, and then estimate calculate Sherwood number, and from the Sherwood number we can find mass transfer coefficients. Okay, but these are the correlations. Still we also said that there are some theories, and these theories are used to find out how does the mass transfer coefficient may depend upon, say, diffusion coefficient, etc. So there are three theories. Let's note down these three theories. One is very popular, it's called film theory. Second is surface renewal theory. Very similar or extended form of this is known as penetration theory, and third is boundary layer theory. Okay, so what we will do now, we will go through these 1, 2, 3 theories, and we will stay away from rigorous mathematical representation or mathematical derivation. Instead of that, we will see what are the main postulates or the fundamental postulates of these theories. So the most common theory here is film theory. Okay, and the main postulates of this theory is that we assume that there is a steady state. One, we have stagnant film. So we will talk of this stagnant film, which is kind of hypothetical film, and we assume that concentration here in this film is linear. So all this theory says that if we have an interface, say we have gas and liquid, then there is a hypothetical film which is stagnant. So when we say stagnant, we are saying that in the component which diffuses in this directions A, we have the bulk flow which is 0, NB equal to 0 here, and the concentration gradient, so say starting from Cg to this interface is linear. So we have Cg, and sorry, this is interface Cg here, we can write Cgi, and we have this Cl which is bulk concentrations. So we are introducing this terminology that there is a bulk concentration of diffusing species. All right. So what this theory says, let's see physically, that if you have interface of gas and liquid and some species diffuses, say sulfur dioxide from air into water, then we have a hypothetical film. All right, this film is stagnant. There can be a flow parallel in this directions, that's possible, but the direction of this diffusion flux in A, there is no bulk transport. All right, so stagnant film means no bulk transport. Okay, no bulk transport. So the first main postulate here is that there is a steady state. All it means the concentration gradients starting from Ci of CGI to this CLB is linear, it does not change with time, and there is a hypothetical film which is a stagnant, in which we can assume there is a diffusion resistance over this, or there is a diffusion length del Z over which concentration drops linearly from CJI to CL. As a consequence, we can write that diffusion flux Na still equals to mass transfer coefficients Km into del C. So this del C is nothing but CGI minus CL into bulk. Okay. So if you go back to the previous slide here, the concentration drops from CGI to CL bulk, which means now there is no gradient within the bulk of the fluid. So whatever there is a resistance, whatever is a drop in the concentrations, it's within this hypothetical film. So we are still writing Na equals Km into del C as a definition for mass transfer coefficients, except one can show that this Km equals DAB over del, or at least this is approximated as mass transfer coefficient as diffusion coefficient of AB over this film thickness or diffusion resistance. So we have a steady state concentration profile 1, this does not change with time, it's a linear, and there is a hypothetical film of diffusion resistance in which we can say that all concentration drops, entire concentration drop occurs over this film of del Z, or which is equal to here, use as a notation for this in this expression here. So there is no concentration gradient here, and we have CGI, and we have this bulk concentration which is CLB. So this all we have this film theory. Okay, so very common, very popular film theory, and it's widely used, but it has only its limitations. And we said earlier that there is no bulk transport in this. So if there could be a flow in this direction, that's permissible. So we can have a flow in this direction, but in the direction of diffusion flux, what we are writing here Na, there is no bulk transport, there is no convection, etc. The second most theory is penetration theory, or we will see that it's a surface renewal theory, which is also quite popular. And here the main fundamental postulate is that concentration profile within that film or within the system is not steady, it's unsteady state. And the main fundamental behind is that this postulate is that, or the mechanism is that, the contact time between the two phases, gas and liquid, is very short. In other words, the contact time is so short that there is no time for a concentration to reach a steady state. So if we get into this physical aspect of this, so let's start with this 2, which we can call it penetration theory, and we will see that this penetration theory or the surface renewal theory is quite similar. There are some restriction here, I will discuss this later. This was originally proposed by Higby. Okay, so all penetration theory says, first, steady state profile, concentration profile is not possible, because time of exposure of fluid, to mass transfer is short. Okay, so look at the difference here, that we don't have a steady state unlike in the film theory. And why? Because time of contact is very short here. So if you go back to the same situations what we had earlier here, that we have gas and there is a liquid here, so still we have a diffusion resistance embedded or over this diffusion length of del Z. Now there is and we have a bulk concentrations which we can still use the same nomenclature as CLB, and this side if we have the concentrations of CGI, this is the liquid phase and this is your gas phase. So as per the penetration theories, there are ADs. Okay, so you have some idea of this ADs from hydrodynamics. Turbulent, very high Reynolds number. We have these ADs which move within the bulk of the fluid. Okay, so they keep on moving within the fluids, and penetration theory says that these ADs, they come to the surface, they spend some time here, and then they go back to the bulk. So this is the time we are talking, the contact time, which is very short. And now this time is so short that concentration profiles which develops between CJI and CL, it does not remain steady or linear, and it changes with time, etc. So these are the main postulate which could be very realistic. Suppose we have carbon dioxide or sulfur dioxide, and we have this water here. There is a flow, we have high Reynolds number, so that there is a turbulence, and we have these ADs. So these ADs continuously they move within the fluid. As per this penetration theories, the ADs come here, they spend some time, they go back to this bulk concentrations, to this CGI concentration, whatever we have in this gas phase. All right. So without getting into too much of this mathematical derivations, one can show that one can write an expressions for unsteady state concentration profile, which can be written as DAB del square CA over del Z square. So the main idea is that this is unsteady state, and with some initial conditions and boundary conditions, one can come out with the expressions for. So now if we have gas here and the situations over, one can come out with the expressions for Na in terms of mass transfer coefficients and Cji minus CLB. All right, but one can show that this KL turns out to be that square root of DAB over pi theta. So what we obtain here, that mass transfer coefficient is actually square root of diffusion coefficients. So there is a fundamental difference between the penetration theory and film theory. In the film theory, we saw that mass transfer coefficients is proportional to diffusivity. Here we are obtaining a relations where it says that mass transfer coefficient is a square root of diffusivity. Now when we talked of this correlations of Sherwood number as A, Reynolds number to the power A, and Smith number to the power B, it's important to point out that nu over DAB. So if the theory says that half proportional to this, one can make an estimate for this B here, and then can solve only for A and A, so that expression for Sherwood number is simplified in terms of A and A. Okay, so these are the theories one makes use of, in obtaining a correct relations or certain correlation between Sherwood number and Reynolds number and Smith number. Okay, the third an extension of this, we said that penetration theory, there is another theory which is surface renewal theory. Surface renewal theory is a bit more realistic than penetration theory, although the main postulate is here is the same. All this theory says, this theory was actually proposed by Danckwerts. Okay, and here it says that in the previous penetration theories, contact time was short, of course, but it was uniform, constant. Here there is a distribution of this contact time. All it means, certain ADs spent theta 1, certain ADs spent theta 2 times, certain ADs spent theta 3 times. So, but still one can show that here also mass transfer coefficient turns out to be a square root of diffusivity into half. Of course, if we go into further details, then there is a parameters which is S, which is called fractional rate of replacement. So there is a rate at which the surface is renewed because of these ADs. So one more parameter comes into this correlation, but our idea is to show that here also mass transfer coefficient is proportional to a square root of this diffusivity. Okay, now let's come to the third theory, which is boundary layer theories, and I'm sure in the hydrodynamics or momentum balance you have heard of this. Over a flat surface, if it's approached by a fluid, then there is a thin boundary layer. in which we can say that resistance to momentum diffusion, all resistance to momentum diffusion is embedded or is confined to this within this boundary layer. Okay, so similar to momentum boundary layer, we also have mass boundary layer, we also have thermal boundary layer. So again, we stay away from this mathematical derivations. One again starts from Navier-Stokes equations in laminar flow. Okay, we can write down the energy balance, we can write down a species balance, and we can calculate the flux as long as velocity profile is known, which is true in case of laminar flow. So let's get back. Let's start this. So in boundary layer theory, you have a solid surface, and it is approached by fluid, say at constant velocity u0, and maybe it has a some concentration Cs0. So if you recall from momentum from your boundary layer theories, there is a thin boundary layer, okay, momentum boundary layer, in which the velocity profile changes from no slip 0 velocity to this bulk velocity, which is u0. So all we are saying that resistance to momentum diffusion is within this del m, and it varies from 0 to this u0 velocity. So similar to this boundary layer, momentum boundary layer, there is also a mass boundary layer, which could be thinner or could be as thick as this momentum boundary layer. So we don't get into much of this detail. So suppose this is your mass boundary layer, which is now del C. So now we are saying that, say the velocity profile is still, say, laminar. So still we have the same starting from 0 to u0. There will be concentrations gradient here also. Now that will vary from some surface concentration Cs to this bulk concentration, which is Ca0. So again, resistance to diffusion is embedded within this del C. This is your now diffusion length del Z. Okay, and if you are asked to calculate this flux in A, either to or from this, so we can have this plate which has some concentration. Maybe this plate is plate dissolves into this bulk of the fluid, which has far extreme concentration at Cs0. So surface concentration changes is Cs, and within the bulk or within this del C, it changes from Cs to this Cs0. One can again write down this species balance quite rigorously. If we have this laminar flow, if you know the velocity profile, we can do the integration to calculate this analytically, diffusion flux. If you have the turbulent, of course, we can make an analogy and we can come out with some correlation there also. So if one can show here also that it can be shown that this Na will be again equivalent to some mass transfer coefficients into this concentration drop, which is from, say, Cs minus Ca0, or we can put minus here because Ca0 is larger than Cs. So if you have the diffusion flux like this, Na equal to minus Km, which can be equated to minus dAb del Ca over del Z at Z equal to 0. So we have this Z directions and this is 0. So analytically one can solve for Ca as a function of height Z, and then we can, once we get a concentration profile, we can integrate this, we can calculate this diffusion flux, equate this Km to Cs minus Ca0 to obtain another correlation for Sherwood number as Kc L dAb, and this would be some correlation as a function of Reynolds number, local Reynolds number, and Smith number, etc. So idea is that all these theories are used to get an expression for Sherwood number in terms of how does mass transfer coefficient varies with this diffusion coefficients. All right. So these are the theories. More than there's some theories, beyond this three theories which we discussed: film theory, penetration theories, or surface renewal theory, and boundary layer theories. But these are the most common theories which are going to be applied in our this mass transfer to, etc. So idea is that again, whenever you are solving a real problems in mass transfer, whether it's a flow in a packed bed or your mass transfer over a flat plate or you have the interface of gas and liquid, okay, you're supposed to go through the table of Perry's handbook or the table and get the correct correlations, calculate Reynolds number, calculate Smith number, or any other restriction which has given to ensure that you are using the correct expressions for Sherwood number to calculate this mass transfer coefficients. All right. So this is the end of your introduction to your diffusion and mass transfer. We take up another topic which is also very fundamental of your calculation or your design aspects. Now, so far what we discussed was one film. So we have gas and the liquid. Okay. In reality, we have flow of the gas, we have the flow of the liquid. So we can think of an interface of two phases. Could be gas liquid, could be liquid liquid, could be liquid and solid. Okay. And we can have a resistance in both the phases. Okay. So essentially, we are trying to combine the two resistances. And so this topic is a new topic here. We call it interface mass transfer. So we have interface mass transfer here. Okay. So this will be an extension of what we did in the earlier. We talked about this hypothetical film. So now if we say that we have two phases, liquid and gas, both have certain Reynolds number, for the liquid, and we have Reynolds number for the gas. There are again we can have now two resistances, diffusion resistance, one in the liquid phase, one in the gas phase. So we can have del 1 and we can have del 2. So two diffusion resistance. Suppose this is your sulfur dioxide and this side we have water, and this sulfur dioxide diffuses from across this interface. So interface mass transfer, again we will have a bulk concentrations. So this concept of bulk concentration was defined earlier. We have Cb, okay, or we can say diffusion species is A in gas phase. So this is your bulk concentration of sulfur dioxide in air. So maybe this is 1% or 0.1%. Okay. So bulk concentrations, and now we have brought in contact with water. Okay, and water, maybe here we have Ca in the liquid phase, bulk concentration, which is quite zero, small, or could be some numbers which is given here. So when we say interface mass transfer diffusion, all we are trying to say that now the concentrations, now that will drop from here from Cag to an interface concentrations, which we can say it's Cai. Okay. So concentration now drops from here Cag to Ci, or for the gas phase we can say that it drops from Yag to Yai. Okay. So now the concentration drops at the interface. Now within the liquid side there will also be concentration gradients. So concentration will also drop from some interface concentrations. We can denote as Xai, so X for liquid phase, Y for gas phase, and then we have again bulk concentration at equivalent to this Cal as Xal. Okay. So now we are talking of four concentrations. One in the bulk phase. So that's the concept of a resistance. All resistance is confined to this del 1. So concentration drops. Okay, let's not worry about whether it's a linear or there's some profile, because ultimately we are going to work on this concentration drop from here to here. Film theory, of course, will say that this concentration within the film is linear. So now we have four levels. One is bulk, Yag, Yai, and now we have liquid phase concentrations, which is now Xai, and then it drops to another resistance here before we have this bulk concentration at X of A in the liquid phase. Okay. So now we have four concentrations. And interface mass transfer, it says that at the interface, we assume equilibrium equilibrium between two phases, which means YAI, the gas phase concentrations at the interface, is in equilibrium by some correlation, by some relations with this liquid phase in the mole fraction at the interface. So this is what we are assuming, there is an equilibrium at the interface. However, there is a transport, there is a diffusion at Na. So sulfur dioxide diffuses from gas side to the liquid size because of this concentration gradient in the gas phase and within the liquid phase. At the interface, however, there is an equilibrium, YAI as function of some XAI. Okay. So before we go further into this mathematics of this, let's try to understand that we have defined two concentration levels. One, we have called it bulk. Okay. So when we say bulk, we are assuming that there is a uniform mixing, so that we have one concentration level either in the gas phase or in the liquid phase. So sulfur dioxide is 1%, 10,000 ppm. So it's constant at 10,000 ppm. Now we have water, pure water. Okay. So as the water trickles down, of course, to start with it's zero concentration, but as it goes along, this will get contaminated with sulfur dioxide, which diffuses from one direction to another direction. However, whatever concentration we have at any level of, say, this absorption column, it's a constant. So we have two bulk concentrations, one in the gas phase, one in the liquid phase, and in between we have an interface of gas and liquid. Interface mass transfer says that now there are two diffusion resistances, one in the gas phase, one in the liquid phase, del G, del L, del 1, del 2. Okay. Concentration, since it's a diffusion resistance, all resistance will drop over this resistance. So now concentration in the gas phase drops from Ca bulk to Cai, or mole fractions. If we convert into from concentration to mole fractions, it's Ya bulk to Yai. I is the notation for diffusion, for the diffusing species, which is sulfur dioxide. So we have Yag, Yai, and in interface we have another concentration in the liquid phase, Xai, and then it drops from Xai to Xa bulk. So 1, 2 bulk concentration and 2 interface concentration. Why there is a diffusion? Because there is a concentration gradient. So we can apply diffusion Fick's first law. There will be diffusion flux proportional to a mass transfer coefficient here. Whatever we have in the gas phase multiplied by the concentration drop, Cag minus Cai. And this flux will also equal to what we get in the liquid phase if there is a steady state. So what we get in the liquid phase is another mass transfer coefficient multiplied by the concentration drops or mole fraction drop within the liquid phase. So there is a diffusion because of gradient within the two films. All resistances of diffusion are embedded within these two diffusions. What happens at the interface? Interface we have thermodynamic equilibrium. A concentration of gas phase at the interface of gas and liquid is in equilibrium with this Xai concentration. Okay, so there is some law there, equilibrium law says solubility. If you have ammonia, we have sulfur dioxide in atmosphere with fixed pressure and temperature, then given pressure, partial pressure of sulfur dioxide in atmosphere, liquid, if we take water, will have a maximum or a prescribed solubility given by thermodynamics. If we take liquid, say liquid extraction, which we did earlier, where we had kerosene or we had nicotine in water, and we wanted to extract from by using this solvent kerosene. So there also there will be an interface, and at which the interface concentration will be decided by the solubility of nicotine in kerosene or nicotine in water phase. So one has to do this batch experiments, equilibrium study to obtain this some kind of equilibrium relationship, thermodynamics. If you have the solid and gas adsorptions, in that case also we have some kind of equilibrium, we call it adsorption isotherms. So first we establish, our strategy is that first we establish this equilibrium concentrations. We do the equilibrium study separately, experimentally, or maybe it's documented in the literature, that given so much of phase concentration in one phase, mole fractions or this concentration or the partial pressure, what would be the equivalent concentration at the interface under equilibrium. Then we apply this diffusion flux. So now let's go back and get into this mathematics. Okay, so we said that we have this interface. Let's draw it one more time. We have diffusion resistance. All resistance is embedded here. This could be like this. This could be like this. In some cases, it's possible that we have concentration like this, and then maybe it's higher at the interface and like this. So phase 1, phase 2, this phase 1, phase 2. These two are the equilibrium, this interfacial concentrations between the two phases here and here. Now whether it's larger or smaller or larger, it's just an artifact of density. So let's not worry that artifact of densities of two phases. Okay, it's possible. So all it still we have, say in this case, diffusion from right to the left. Na diffuses like this. Here also it diffuses from right to the left. So this doesn't mean that we have a diffusion from lower concentration to higher concentration. More important is that what happens within this film here and here. There is a concentration drops from here to here and from here to here. At the interface we have equilibrium. At the interface we have equilibrium. Still there is a diffusion because of this gradient from here to here and from here to here. Whether this one is higher than this, whether phase 1 has higher concentration or the lower, or lower than higher, or here in the opposite, in the just reverse direction, reverse way, it's all the artifact of density of two phases. This could be a denser phase, this could be a lighter phase, this could be a lighter phase, or this could be a denser phase. That's not important. Or we are saying that interface concentrations yi has, there is a thermodynamics which says that the two are in equilibrium concentration. So one has done this batch experiment or some reported data where knowing xi we can calculate yi, or knowing CAL we can calculate CAG in the gas phase. Okay, or in case of say liquid solid, knowing how much is the concentrations in this liquid phase, we can calculate how much is concentrations in the solid phase. So this is called isotherm. In case of gas liquid, this is nothing but your solubility data. So if you fix say pressure and temperature, total pressure and temperature, then one can vary this concentration in the liquid phase to calculate gas phase, or given gas phase we can calculate this liquid phase concentration. So these are all used to determine this interfacial concentration, which we say that interfacial concentrations, which we say that they are, the two species are at equilibriums at the interface. Okay, although there is a concentration gradient within the bulk, within this film, diffusion flux. Okay, so now if you understand this, now we can obtain in expressions assuming a steady state. So if it's a steady state, whatever diffusion moles per second per meter square we have in the gas phase will also be same as moles per second per meter square in this liquid phase. So we know already, we know the expressions for Na in terms of mass transfer coefficients and the concentration drop. So all we do, we equate. So we can write Na moles per second per meter square equals Kg. So if Kg is mass transfer coefficient in the gas phase, this will equal to what we wrote earlier. We have mole fractions of A in the bulk phase, so YAB minus YAI. So this is your Na. Under steady state, this diffusion flux will also be same as Kg KL. Now XAI minus XAL in the bulk liquid phase. Here we can say, if we are using the previous nomenclatures, this is nothing but YAG. And YA and XI, they are in equilibriums. This is given by some equilibrium data, okay, which we have obtained from some experiment or from some reported values. This is nothing but solubility in some case. If you're talking of absorption of ammonia in water, is nothing but solubility data. If you're talking of absorption of sulfur dioxide on some solids like charcoals, then we'll call it isotherms, or to be more precise, adsorption isotherm. Adsorption isotherms. Okay, so all we are saying that under steady state there are two diffusion resistance given by Kg and KL. So you recall Kg, KL, both will be proportional to diffusivity, diffusion coefficients, either in the gas phase or in the liquid phase, over this film diffusion distance del z, which could be del g or del l. So we have two mass transfer coefficients proportional to diffusion coefficients. If you apply certain theories, if it's a film theory, it's proportional to DAB. If it is surface renewal theory, then this is DAB to the power half over this del z, which is either del g or del l. Okay, so by this interface mass transfer, let's summarize here. All we are trying to say that interface mass transfer, it says that interface concentration, that's an equilibrium, and under steady state two diffusion flux are the same, and they are proportional to mass transfer coefficients in the gas phase multiplied by the concentration drop in the gas phase, will also be equal to mass transfer coefficient in the liquid phase multiplied by concentration drop in the liquid phase. That's it. We have two correlations for two equations, one for gas phase and one for the liquid phase. Interfacial concentration yi and xi, they are related, and we have one more equation. So we can say equation 1, equation 2, and we have equation 3. These three equations will decide the diffusion flux, and we will take up this graphical representation of this. So let us make some graphical representation here and also do some calculations. So first is we have a plot for y versus x. Okay, so this is, let's say it's our equilibrium curve, and let us not worry whether we are discussing absorption or adsorptions or liquid extractions. We have been given this equilibrium curve at one pressure, constant pressure and constant temperatures. So equilibrium curve says that given x, this would be y in one phase. Suppose we have a liquid, then this will be the concentration in the gas phase under equilibrium. So all it means, if we want to obtain this curve for absorptions, we will be doing a very simple experiment. We'll bring water. If water is a absorbent, and we will have this ammonia or sulfur dioxide gas at certain partial pressure or certain concentrations or certain mole fractions, and they will be brought in contact for a long time with water. We can put some stirrer here. So after a long time, we have to measure what is the concentration here in gas phase and in the liquid phase, or mole fraction in the gas phase or in the liquid phase, and obtain this data point. Next, one can again vary this partial pressure PA and can again bring in contact with the fresh water, wait for the equilibriums till we have another points. So we have obtained all these data points for equilibrium curves. Okay, in case of the solid and liquid, or solid and gas, we will be doing the same study. The idea is that we have obtained this equilibrium curve. Okay, and we wrote that there is an interface, two resistances here, concentration drops like this to this. So let's use the nomenclatures. Maybe this is a gas side, this is a liquid size, A is a diffusing species, YA we have B, bulk concentrations, we have YAI, we have XAI, and we have XAB. So two phases here, liquid and gas. And how do we, and we write the expressions for Na once more. Na under steady state will be Ky. So Y is for gas phase will be equal to YAB minus YAI equals Kx XAI minus XAB. So under steady state diffusion flux across this film, both the films liquid and gas, they are the same. Okay, which means we can write now Kx over Ky equal to YAB minus YAI over XAB minus XAI, and we have minus Kx over Ky. So all we know, the ratios of mass transfer coefficient in one phase to another phase, and kx and ky, which are obtained from Sherwood number in gas phase or the liquid phase, and this will be shown to be this has been shown to be a function of Reynolds number and maybe the Smith number for the gas phase and the water phase. Okay, so now let's plot again these points on xy plot. So we have xy, we have equilibrium curve here between y and x, and this is our bulk concentrations given in gas phase and water phase. So now we can say that we have x A bulk phase B, and here we have y A B the bulk phase. Okay, and let's keep this interface in mind. Here we have 1 and we have this 2. So YAB is here and XAB is here. Okay, all we do, realizing that mass transfer coefficient ratios is given in terms of interfacial concentrations YAI and XI, we can take a slope of minus kx over ky, because kx over ky has been shown in terms of YAB, XAB and YAI and XAI. So knowing these 4 concentrations, we can calculate this ratios of minus kx over ky, and we can plot this. Alternatively, if we know the mass transfer coefficients, then we can know the bulk concentrations YAB and XAB. We can mark this point, we can take a slope to reach this concentrations, which is nothing but XAI and YAI. Okay, so let's try to understand this again. We start with the equilibrium curve. One, this is given from thermodynamics. So we have already done this experiment, batch experiments, and we have obtained this solubility curve or isotherms, or we know the relation between y and x at the equilibriums. What we know is possibly the bulk concentration, because we can measure sulfur dioxide is 1% and how much is the water concentration of sulfur dioxide. So we know this point here. Now if we know the operating conditions, say Reynolds number and a Smith number, Reynolds number and a Smith number in the gas and liquid phase, we can calculate kx and we can calculate ky. Once we know kx, ky, we can take the ratios and we can plot this minus kx and ky to reach this interface concentration, which is YAI and XAI. Or if we know this XAI and YI, then we can join this line, and then the slope will be given by minus kx over ky. So either way it's possible. All we have done, we have represented the same statements, that under steady state diffusion flux in the 2 phases are the same, and they can be represented in terms of the 4 concentrations, 2 bulk concentrations and 2 interface concentrations, one in the 1 phase and the other in the 2nd phase. If we equate the 2 rates, we will get what we have shown here as a graphically, one concentration here YAB, XAB and YAI and XAIs. Okay, and so we have marked the coordinates, we can plot this curve. And now the problem comes here, that what is this interfacial concentrations and how we can measure it. It's very difficult. If you have a flowing system, then we have gas phase, say sulfur dioxide goes from the bottom to the top and water trickles from the top to the bottom, and we have the interface, right? If you are asked to measure the concentrations, all we can do, we can take the samples of gas from the bulk or the samples of liquid from the bulk. It's impossible to reach this interface concentrations. At least maybe some other techniques we'll have to use to how do we find the interfacial concentrations, because the moment we take a probe and try to reach the interface concentrations, it will spoil the concentration profile, it will spoil the hydrodynamics, etc. So all we're trying to say that it's the bulk concentrations which can be measured. Interfacial concentration cannot be measured. One of course goes by this thermodynamics. It says that yes, for a given XAI, YA is fixed. If I change XAI here under equilibrium, interface concentration will be so much. If my interface concentration in the gas phase is so much, then in the water phase this will be so much, or we know the relations between YAI and XAI. Absolute values in a running in operating system is not possible to do it, which means we have to think of some other ways how we can calculate this flux. All right, to calculate the flux we need kx and concentration drop, or if we write in terms of mole fractions, then we have kx into del x, or we have ky into del y. Del x and xy is bulk minus xi, or we have y bulk minus yi. So these are not known to us, it's difficult to measure. So we will think of defining another coefficients, we will call it overall mass transfer coefficients. Overall mass transfer coefficient. So what we have is individual mass transfer coefficients, individual or film mass transfer coefficient. Okay, there's no harm, one can still calculate kx, ky given Reynolds number and Smith number, but now we all we know is the relationship between y and xi. Okay, but since we do not know the exact value, individually xi's and yi's for our design calculations, we need another definition here, which is overall mass transfer coefficients. So let's see what is overall mass transfer coefficients. We have x and we have y, we have the equilibrium curve, we have here y, a, b bulk concentrations, and the coordinate here is x, a, b. Okay, if we know the two mass transfer coefficients, individual mass transfer coefficient, we can draw a slope of minus kx over ky to obtain xai and yai. This is what we did so far. Now let's define two more concentrations. For a given YAB, there is another concentration given by the equilibrium curve. So if YAB is say 1000 ppm, if P and T is fixed, we have equilibrium curve fixed, we can also get another concentrations level here, which would be in equilibrium with this YAI. Okay, so we have x A, we will call it a star. So what is x A star? It's an equilibrium concentration in liquid phase given bulk concentration of YAB. Okay. Similarly, if we have XAB here, given this XAB, we can get another concentrations here, which we can call it YA star. So what is YA star? It's in a concentration in equilibrium with XAB. But it's very important to note that in reality we have one YAB, XAB. These are the two physical or measurable concentrations. Okay. XAI and YI, they are also physical. They also exist at the interface concentration, except we are trying to avoid the measurement of this concentration, which is YAI and XAI. XA star and YA star, these two are hypothetical, they do not exist in the system. So why hypothetical? Because YA star, we are saying that it's in equilibrium with XAB. In other words, if we have a system where interface concentration is XAB, then concentration in the gas phase would be YA star, but we don't have that. We have interfacial concentration at XAI and YI. So it's hypothetical YA star, as if we have XAB in equilibrium with Y star. Similarly, for given YAB, we have another hypothetical concentration here at XA star, as if we have a gas phase at YAB and we brought in contact with this liquid at this XA star, and under equilibrium these are the two concentrations. So if you go back and try to recall, we have a real system of gas and the liquid. Two are the bulk concentrations which are real. Two are the concentration at the interface which are real. We can measure these two, we cannot measure these two. We have been asked to calculate diffusion flux. Thermodynamics says that given one concentration in one phase, we can calculate the other phase concentration under equilibriums. Okay, we are trying to avoid the measurements of XAIs and YAs because these are not the major quantities. So we defined two more concentrations, as if given gas phase concentrations, if the entire concentration is brought to the interface, what would be XA star? Or if we have XAB here, bring the entire XAB to the interface, what would be YA star? So YA star and XA star, these two are the hypothetical concentrations. Okay, but nonetheless we will see that we will define a quantity which we said overall mass transfer coefficients, which should be very handy in the design calculations. Instead of working on the individual mass transfer coefficients, generally we prefer to work on overall mass transfer coefficients. Okay, so now let's write down the similar equations for Na. We wrote Na equals x, we wrote under steady state we can write Na equals Kx xAi minus xAb, which will also be equal to Ky as YAB minus YAi. Okay, we can also define, so this is, you can call it definitions of mass transfer coefficients in X phase or Y phase or liquid phase and the gas phase. One can also define as another overall mass transfer coefficient which will denote by K, or sometimes is denoted by K overall, KOX and KOY. So maybe we draw slightly bigger here. This is your Kx. Now we can define as Kx as XA star minus XAB equal to capital Ky YAB minus YA star. So look at what we have done. We have avoided using interfacial concentrations. Instead of that, we are using two quantities, XA star and YA star. What is YX star? It's in equilibrium with YAB. What is YA star? It's in equilibrium with XAB. So these two are hypothetical. In reality, bulk liquid phase and the bulk gas phase, they don't see each other. They are miles apart. We have the interface here. Okay, so we have the bulk concentration of gas and the liquid here. They don't see each other. What they see at the interface, what we see is the interfacial concentration, XAI and YI. But we don't want to use that because that's the interfacial concentration that cannot be measured. Bulk concentration we can measure. So to avoid that, we define these two hypothetical quantities, YA star and XA star, as if we bring the entire liquid in contact with the gas, we will get YA star from thermodynamics. Or if we bring entire gas in contact with the liquid, we will get XA star from thermodynamics. Now we have all pure mathematical expressions, 4 equations, and we'll see how many unknowns here. We can equate this to obtain 1 over KOY equals 1 over KY. This KOY is same as KY, capital KY equals to small 1 over KY plus, we will see, we'll call it M prime over KX. We'll come back to this. What is this M here? We'll make use of the graphs for the interpretation of this Y M prime. This also equals, we can write KOX, which is nothing but capital KX equals 1 over small kx plus 1 over M double prime into KY, where M dash and M prime is given as YAI minus YA star over XAI minus XAB. Similarly, M double prime equals YAB minus YAI over XAI minus XAB. So this is all by mathematical manipulations of these 4 equations. If try to eliminate one from the other, one can show this as an expression for overall mass transfer coefficient in terms of individual mass transfer coefficients through these interfacial concentrations and the bulk concentrations. Okay, of course m dash prime doesn't equal to m double prime. However, in the limit one can show that this is nothing but the slope of this equilibrium curve. Okay.